Okay, so welcome all, and it's a great pleasure that we start our next appointment for the cotangent, for the Fellowship of the Ring. And today we have uh, Srikanth Iyengar that will give us a fantastic talk about cotangent homology or commutative algebra. So I know that you're all, looking forward to this. So let's start, Sri.
Thank you, Claudia. So anyway, so this, as the title says, it's going to be about the cotangent homology of commutative algebras. So this is part of a project that has been on my mind for the past 20 years or so. And maybe the main progress I have to report is that I picked up two very clever co-authors, one per decade. Before I get to the new stuff, I'll spend quite a bit of time on, I try to give at least a rough lay of the land. And the basic references for my talk is this beautiful notes by Herzog called Homological Properties of the Module of Differentials. It's based on a lectures he gave in Recife in Brazil. I don't think it ever appeared formally, but Ben and I are preparing some annotated version of these notes, and it'll appear under Jorgen's name in a volume dedicated to Volmer Vasconcelos. I gather Jorgen was intending to do so. Okay, and the other two references are a paper that Ben and I wrote a few years ago, and Avramov's famous notes on infinite ray resolutions. Okay, so let me get started. So throughout K I'll be working over a field K, and I'll assume that the characteristic of K is 0. So maybe K is irrationals or reals or whatever you like, whatever favorite field you like. And to keep things simple, because things are already complicated at this generality, I'll assume that I'm working with finite type K algebras. So this is a finitely generated K algebra. So basically a quotient of a polynomial ring over K yeah. And then let me also fix a map of such K algebra. Right, so in particular, S is also a finite type over R. Okay, so attached to this, such a map of K algebras or such a map of rings, there's something called the cotangent complex, which I would like to denote today like so. So this is the cotangent complex of phi. And this is a complex of projective modules. So this is starting in degree 0. These are finitely generated projective S modules. And this complex is well defined up to homotopy. So it's well defined in the homotopy category of projective S modules. Right? It's only well defined up to homotopy, but that's enough for what we need. So the degree 0 part of this is the usual module of Kähler differentials. And one can think of L as some sort of derived Kähler differentials. And I want to, at least in this context, L of C is derived Kähler differentials. So I want to try and explain what this means. So sort of give you a construction of the cotangent complex in this context. So what you do is you start with, so the construction is as follows. So you start with what one calls a model for S as an R algebra. So this is what is called a model. So what this is that X is going to be a graded set of variables, non-negatively graded. R is the free graded commutative algebra on this. So Rx, the model itself. So this is going to be the symmetric algebra on the variables of even degree, and exterior algebra over R, of course. on the variables of odd degree. So it's just a free algebra. So it has a differential, which is R linear and satisfies the Leibniz rule. In other words, Rx is a DG algebra. What's happening here? It seems to be stalling. Sorry. Give me a second. Something went wrong with my iPad.
Don't worry, give you a second, no problem.
Yeah, it's supposed to be a second page. Hang on, let me just shut it and start it afresh. Maybe that takes care of it. Nope.
Maybe
I don't hesitate to ask questions as and when I go along. And I noticed that Ben is in the audience, and he should feel free to correct me if I say something wrong. When I say something wrong. Okay, so let's see. Oh, nothing is here. That's odd.
Because it's much ahead the page. I think you went very far.
Okay, let me.
By moving it. So you can go to, yeah, exactly.
I think it's completely messed up, but all right.
Okay.
So let's see.
Yeah.
Hopefully there are no more technical problems. All right. So as I was saying, a model is nothing but a DG algebra resolution where the thing in question, where did it go? Where the algebra in question is free as a commutative algebra. So it's a free algebra resolution. Let me write it like so. So Rx, actually the technical term is semi-free. Is a semi-free algebra resolution of S over R. Okay, so attached to such Rx, you can talk about the module of scalar differentials, which is going to be, so you know how to compute the module of scalar differentials for a polynomial ring. It's just generated by, it's free over the generators. So this is going to be free on the generators of this algebra. So this is going, and you have one for each x. Now this is all happening in the graded category. So the degree of this is the degree of x. So this is supposed to have a differential. So the differential on this, so there is a differential. A differential such that, so restricted to Rx, it's the old one. It's the differential on Rx. So all I have to do is tell you how to, what it does for these new variables, new basis elements. So d of delta x is going to be delta of dx. So this makes this module of scalar differentials of Rx over R a DG Rx module. And as you can see from the construction, it's obviously free over Rx in some sense. And so the cotangent complex is nothing but base changing everything to S. Okay, and so this is going to be as a free module. If you forget the differentials, it's just the free module over S on these elements delta x. And the differential, of course, is inherited from the differential on the module of scalar differentials for Rx over R. Well, let me just give you a couple of concrete examples, and this will make it clear as what I'm doing. So the first and the simplest is when you take the case when S is just a polynomial ring. And for whatever reason, I'm choosing to change the variables and call it T1 to TD, and this is S. So of course, in this case, S is a model over itself. So this is RT is itself a model. And then the cotangent complex, so maybe I should do it in 2 steps. So if you then do, I mean, there's nothing much to do. So the cotangent complex is nothing but the module of scalar differentials. Well, this was maybe a bit too simple. Let me do one step further. Let me go one step further by looking at a hypersurface in the polynomial ring. And so this is going to be a non-zero device in RT, in the polynomial ring. So this is S. So in this case, the model starts off with, for R, S over R starts off with a polynomial ring, but then you have to introduce a variable to kill this relation f of t. And this is then a resolution of S. This is nothing but the Koszul complex on F over the polynomial ring, right? And in this case, if you compute the module of scalar differentials of RTX over R, so as I said, it is free over the generators. There are two, so you have, first of all, the TIs, I should write delta. For first the TIs, but I'm a plus then the one for X. Well, so this delta Ti has degree 0, so clearly the differential of this is going to be 0. The differential on delta X is, according to the prescription, it's delta of the differential of an X. The differential on X is just f of t, and delta being a derivation, what this is the partials. So this gives you completely the module of scalar differentials of the model over R. So the cotangent complex in this case is going to be, well, there are d copies of S in degree 0 corresponding to this one, and one copy of S in degree 1 corresponding to that delta X. I'm dropping the basis elements. And this is nothing but the Jacobian matrix associated with the partials of F with respect to T. So this is the cotangent complex. And more generally, if you look at maybe this is the third example, if you consider the case where you take a complete intersection over R. FC, where F is a regular sequence, then you can, it's again the Koszul complex as a model. What you have is RT, but then you have X1 to XC. Fi, this is a model for S over R. And if you do the computation, and it's again no more difficult than what we just did, you see that you end up with a complex like this, and here it's a Jacobian matrix of this system. Okay. So of course, this is very special. They're dealing with complete intersections, but if you do more generally, you end up having to kill. Typically, the Koszul complex will not be acyclic, so you will have to introduce variables of higher degrees to compute the model, and correspondingly, the cotangent complex will have more terms. So roughly speaking, the cotangent complex is keeping track. If you're forgetting the differential, it's keeping track of how many variables you introduce in the model for S over R. So I should have said at this point that this is really, I'm talking about ideas of Tate and Gullikson, etc. Okay, so again, so the cotangent complex is just forgetting the differential is keeping tab of how many variables are needed in the model to construct S over R. And the differential is, as you see, just keeping track of the linear part of the differential on the model. Okay, So this is the construction, a quick summary of the construction of the cotangent complex. By the way, all this worked because I was in characteristic zero. If I was not in characteristic zero, I would have to use some simplicial models to compute it, which one reason I've stuck to characteristic zero, but not the only reason. Okay, so now, before I move on, let me introduce these homology modules. So for any S module, so this is by definition the homology of the cotangent complex with coefficients in n. And later I'll also talk about the cohomological version, which is the cohomology of the cotangent complex coefficients in S. This is, of course, the under-equivalent cohomology modules. All right. So what are the basic properties? Let me just recall the basic properties of these things. So already by construction, D0 is scalar differentials tensor with n. And if R2S is surjective, then D0 is going to be 0, and then D1 is I mod I square tensor. So that's one feature of this. The second feature is that if you're given, say, Q to R2S, maps of K algebras, by the way, the K has not played any role so far except to ensure that all the rings in question are defined over a characteristic zero field. So we have the Jacobi-Zariski sequence attached to this. It starts off with, let me drop, well, it's D naught S. Let me write instead. I could also do the version with coefficients, but let me skip that. So we have the scalar differentials of S over R, the scalar differentials of S over Q. And then R over Q, and then here's where you start. So this is an exact sequence, and the failure of exactness is measured by these cotangent homology modules, which is one reason one can think of these cotangent complex as derived scalar differentials. It measures the failure of the JZ sequence to be exact on D1, etc. And it goes on. There's also a cohomological version, but that's suspect. Any questions, Claudia?
Yeah, I don't understand. So the first one is the one of S over R against S. And the second one?
Yes. Oh, yeah. So it must be S over Q.
Okay. All right.
Isn't that correct? I think I got it right.
Okay.
S over R, S over Q, then R over Q.
Okay.
Yeah.
And it goes on like this, and the Q and so on.
Yes. Then you end up with D1 of R over Q with coefficients of S, and then
Yeah.
All right. So this is it. And okay, I guess one reason all this is interesting is because you can detect smoothness. So when R2S is smooth, so flat with regular fibers, if and only if one of this is 0, this is if and only if for all I greater than or equal to 1, and this is if and only if S over R is projective. Let me put it like this. If and only if a cotangent complex is a resolution of the module of scalar differentials. That's just reinterpreting what the preceding line is saying. This line is saying that this cotangent complex has no homology, And that's saying, it's saying that the cotangent complex is concentrated in degree 0, in which case it will be the Kähler differentials.
But don't you have to allow coefficients for the last equivalence?
So here I'm putting blank.
No, but for the last one, the last. The third one, you know.
So you're right, of course. I need to allow coefficient. No, hang on. When I say this, I mean the cotangent complex is equivalent to this, and this is projective. So what this is telling me is that
if you assume projective, okay.
Yeah, right.
Mm-hmm.
Correct. Thank you. And I should have made a comment about this vanishing of the DIs. I'll do it in a second. And then R2S is LCI, meaning meaning that S is we know it's a quotient of polynomial ring over R, but the sequence is locally regular. Regular sequence. So this is LCI. This is if and only if the cotangent homology vanishes for all I bigger than or equal to 2. And this is tantamount to saying that the cotangent complex is equivalent to, it's just concentrated in 2 degrees. LZ, L1 and LZ. Okay. So one can measure these properties in terms of the cotangent homology. Maybe I should have made this remark here before to clarify this. I'm switching between talking about the cotangent complex and andrequilin. And the remark here is that so for any integer, any index I, any degree I, the cotangent andrequilin homology or cohomology vanishes as a functor if and only if the degree I part is 0. What it means is that it is homotopic to a complex of projectives where there's nothing in degree I. Okay, so if you saying that the andrequilin vanishes eventually, or for degrees higher than 2, is tantamount to saying that the cotangent complex is equivalent to something in degrees 0 and 1. All right. Any questions so far? So this is all sort of the basic story about the cotangent complex, and this is by my way of saying that this is why one might care about cotangent homology. There are other reasons, of course, including connections to deformation theory, which is probably, okay, so I want to think about what can we say about the cotangent complex as a complex. So what do we know about it? So the basic question one can ask is, so what do we know about the cotangent? So this section is for me titled, What Do We Know? About the cotangent complex. So the first question you can ask yourself, so if you're given a complex of projectives, maybe the basic question is, when is it going to be perfect? When is this a perfect complex? i.e., when is the cotangent complex equal to a bounded complex? Remember, the cotangent complex for me is always a complex of projectives. When is it equivalent to something where there's only non-zero components in a finitely many degrees? So this is equivalent to saying that as a functors, the andrequilin vanishes in degrees n plus 1 and half. Okay. And one answer to this is was given by Abramov, that if you also assume that S over R is flat, finite flat dimension suffices. Is enough, then the cotangent complex is perfect if and only if is LCI. So we know that if it was LCI, it's only concentrated in degrees 0 and 1. So one way to think about this result is that, so this is from 1999, I think. One way to think about this result is that for maps of finite flat dimension, the cotangent complex, if it's finite, it's actually just of length 2. And there's already one bumps into this conjecture of Quillen from the early 70s, late 60s, that in general, without assumption of finite flatness, if this is perfect, if the cotangent complex is perfect, it must be very short, basically one more than what you have for CI. And it's easy to write down examples where the cotangent complex has length 2. So it has only 3 components. And Quillen's conjecture from the 70s is that this must be the case in general. It cannot get bigger than this if it's finite. And this question is basically open except when this conjecture is basically open. It's the one case where I know this is true is if when this map has a retract. Meaning, so this was phi, so a map of algebras sigma such that phi sigma is the identity on S. So this is something that Lucio and I proved in around 2000. Okay. So this is about the first thing you can ask about cotangent complexes. So when is it going to be finite? All right. So the next question, the next feature you might look at are the syzygies in the cotangent complex. So what do I mean by this? So, right, for each integer n, let's look at the co-kernel of the nth truncation. So this is the co-kernel of the map from Ln plus 1 to Ln. So remember, these are projective modules. If this complex was acyclic, if it had no homology, then this would be actually syzygies, but there is good reason to call these also syzygies in the complex. So these are just looking at co-kernels of these maps. So for example, C0 is nothing but the Euler differentials, and C1 is I mod I squared if you write S as over I, as a quotient of a polynomial ring over I. So you can think of these as sort of higher cotangent modules. So cotangent modules. So then one can ask what we know about these higher cotangent modules. So the starting point is this Jacobian criteria. Which says that if S over R is flat, and if you knew this was projective, this implies that S over R is smooth. Remember, I'm in characteristic 0. So I don't have to worry about being careful about ranks. So at least if for the cotangent module in degree 0, if you know it's projective, then you know the algebra has to be smooth. So then, we actually, Ben and I proved that the same thing holds for any of the something similar holds for any of the cotangent modules. So what we proved is the following. This is in that paper that I mentioned earlier. So assume that this is flat or finite flat dimension, that's good enough. So, and assume that n is bigger than or equal to 1. So if the projected dimension, so these are all finitely generated S modules. Where it go? The cotangent modules are finitely generated S modules. So if you look at, if this has finite projected dimension, this means that this must be LCI. And if you look at for n equal to 1, this was given what I said here, that the first cotangent module is the conormal module of the presentation, this was conjectured by Vasconcelos, and this was first proved by Ben. Yeah. This was Vasconcelos' conjecture proved by Ben. Okay, so this result says that it's true for all the higher cotangent modules. So you'll notice that this is missed out n equal to 0. So the n equal to 0 case would say that if the module of Kähler differentials has finite projective dimension, then it must be regular CI, or if you know it's CI, then it would be smooth. Well, even that is not so clear. So this is, of course, still open, and it's connected with this Heisenberg-Mazur conjecture. And in fact, this was conjectured by Jürgen Herzog in those notes from Brazil. I'll get to that in a bit. So this is about the cotangent modules. Oh, I should mention one thing. How do you check if these cotangent modules have finite projective dimensions? So suppose you knew that there was a gap in the cotangent complex. Then what you see is that you have Ln, so which is 0, Ln minus 1.
Can I ask a question? Can you go back?
Yes, of course.
Yeah. So here you get that the projected dimension, let's say, of C3 of phi.
Yes.
Is finite when it's locally complete intersection. But you said that if Asarov was flat by Avramov, and it was locally complete intersection when there was only C0 and C1, no?
What is it?
Understood that wrong.
What is it? Correct. So if it is CI, then the only thing you see is C0 and C1.
So actually, the C3 if it has projected dimension finite is 0.
Yeah, it'll be 0 basically. Okay, yeah,
zero.
That's correct.
It has to be 0. Okay.
Correct. So I was going to link up to what Lucho proved, but you're absolutely right. So back to what I was saying, so if suppose there was a hole in the cotangent complex, so suppose Ln was 0, so this tells you that first of all, Cn is 0. And it also tells you that Cn minus 1 is projective. Right? So if you see from here that having a hole in the cotangent complex, which is tantamount to saying that the under-equivalent vanishes as a functor, this already one vanishing implies S over R is locally complete intersection. So this result that I mentioned with Ben.
Only if S over R is flat, though, no?
Oh, we always need this flat or finite flat dimension.
Yeah. Okay.
Yeah, that's always the case. Yeah. So all these results are under those hypotheses. If you don't have flatness, the only result I know is about this one with Lucho, which says that if the cotangent complex is eventually 0, then it must be. Yeah. And actually, the same argument also says that if you have a retract and just one vanishing also forces it to be in P, then 3. Okay, so this tells you that some of the results with Ben capture also Avramov's results. They subsume Avramov's results. Okay, so this is all about the syzygies in the cotangent complex. So the third thing that you can start looking at, and this sort of brings me closer to new things, is to look at the homology of the cotangent complex. So namely, I want to look at the André-Quillen with coefficients in S. And let me abbreviate this to, I'll just drop the coefficients because from now on, I'm going to focus on this, which is the nth homology of the cotangent complex. So of course, we know some things about this. When R is CI or smooth, there's not so much to say. The question is, what do you know about the homology when the map is not CI? And this is where we encounter this conjecture due to Jürgen Herzog from those notes. So I think it's 1981. So what Jürgen conjectured is that, again, okay, so it's a slight variation on what he said, but he said, let's suppose this is flat. then if this is 0 for all n large enough, this implies that S over R is locally complete intersection. So this is a conjecture. I should have mentioned. So this is a conjecture. Okay, and he also said that this is. He also asked if what we could say if only if you knew all the cotangent homologies beyond 1 or 0. Okay, but I'll focus on this specific version of the conjecture, and the main result here. Okay, so to go further, let me focus on the case when. From now on, let me focus on the case R equal to K, because already here it's okay, and also S is local. Because basically, if you can handle this case, I'm sure we can reduce it to, can reduce the general case to this case. So this is the key important case. And what you proved a beautiful result, and what he proved is that if the Poincare series of each S module is rational of each, of course, finitely generated S module, rational, then the conjecture holds. So this is his. This is, as far as I know, the main result we have towards this conjecture so far. Okay, so if you know that modules have rational Poincare series, then this conjecture is true. This gives you lots of examples, but of course we know that there are rings for which the Poincare series is not rational. And what I want to do next is try and sketch, because it's such a beautiful argument, I want to sketch at least a basic idea of the proof and then tell you what more we can, then go ahead from there. So maybe this is a good point to take a break for a few minutes.
Okay, that's fine. So let's take a break here. And then, since it's 5:40, should we take 5 minutes or is too much, Carl? Okay, so let's start again at, I would say 5:45, okay? In my watch. All right. So 5:45, we start back. Srikanth, this is beautiful. So I want to ask a question. This Herzog result is really just when R is a field, no?
You could reduce it to the case where S over R is flat by standard base change. Actually, Jorgen was mostly interested in the case where S is a quotient of R, where R is a regular ring.
Okay.
If you have that S, the cotangent complex is good. Well, there is a slight. I have a feeling this is the. Am I making a mistake? I don't. Yeah.
But in a certain sense, it says that the complexity of this, because the homology can never be 0, so it says that the complexity of this complex either is very simple, it has 2 terms, or the complexity is very, very, not just is infinite, but it has homology everywhere.
Basically that there are infinitely many non-zero homology groups.
Yeah. So
in fact,
it can never be exact anywhere. Yes.
Correct. Yeah. Yes. Yeah. That's what it is. In fact, as I'll explain later on, we suspect that the story is even depends on your perspective, better or worse. Oh, there was a chat. I see. Srikanth, some other Srikanth is asking if the rational Poincare series has to have common denominator. No, just rationality is enough. In fact, I'll talk about this in a second. Yeah. Give me a second. Oh, where did I go? You can still see. Good. Okay, so I was going to start talking about this Jürgen's argument. Okay, so first of all, there's a lot of things you can say because I'm in the local case, right? So we can assume that you can minimize f. What I mean is that you could, or rather, I can assume L is minimal, the cotangent complex is minimal, meaning the differential lands in m times the maximal ideal. And since it's local, things are free. So then the cotangent, you can speak of the cotangent complex. There's not to worry about up to homotopy and so on. So then you can measure these ranks of the modules that show up, the free modules that show up in the complex. So let me, n minus 1 is an S module, and let me call it epsilon n. There's a shift here for a reason, n bigger than or equal to 1. So these are called the deviations of S. And it's called so because S is regular. From what I've already said, you can see that S will be regular if and only if, okay, I better get this. En is 0 for all n bigger than or equal to 2, and S is Ci. Is that correct? Yeah, I think so. L0 is the embedding dimension. So E1 will be the embedding dimension, it's L0. And then Ci if and only if. So by the way, this is the cotangent complex of S over K. So S is a quotient of a polynomial ring, and you're doing this. So this is the deviation 0 for all n bigger than 3, right? Okay, so this is clearly an interesting sequence of numbers. It's one measure of the size. So Avramov, at least one result of Avramov's tells you that this is connected with the Poincare series of the residue field of, let me assume that it has the same residue field as K. It's not a big deal. The Poincare series of S can be expressed in terms of these deviations. So this would be 1 plus e to the 2y plus 1 and 1 minus, this is why I had to shift this, I bigger than or equal to 0. Okay, so the cotangent complex, remember, records information about the algebra generators of S over K in an algebra resolution. Whereas the Poincare series here is recording information about the resolution of K over S. And what Avramov's result is telling you is that the one ranks will tell you, one determines the other, at least the ranks. More is true, but at least the ranks, okay? So this is one thing. And so now, so what you can do is, so what Jürgen actually says, Jürgen's result is basically that, Jürgen's main result is that if you can also look at the generating series of the deviations, this is Herzog again, though it doesn't quite quote it like so, but this is embedded in his proof, that these two series cannot be rational simultaneously, or rather, if it happens for a trivial reason. This is bigger than or equal to 1 plus this rational. If they are both rational, this implies that this must be the deviations must be 0 for I large enough, which we already know would imply that, because that would tell you the cotangent complex is perfect, right? Because the deviations are measuring the rank. So this is telling you that S is CI. So Jürgen's result is basically that these two series cannot be rational at the same time. And the way he proves it is that he takes this idea is the following. So using the logarithmic derivative of so he uses the rationality using the logarithmic derivative of the Poincare series. So basically the formal derivative modulo P. So it's looking at the too many D's in this talk. This is the usual derivative, assuming it's rational. So by the logarithmic derivative, I mean this rational function. So using this and this, he constructs Jürgen constructs a series, which let me call alpha I ti, with the property that where the alpha I are rational numbers. So this is a rational function. He constructs a rational series with the property that these alpha i's vanish for all I large enough and prime numbers. I are prime numbers. So assuming that, assuming that the EI is non-zero for infinitely many I. So it's not so hard. If I just tell you that, look at the logarithmic derivative, and from here you can easily use these two functions to cook up a rational function with the property that the coefficients of the rational function, they vanish for all prime indices for, you have a question, Carl? No, for all I large enough. And this violates the result of, contradicts the result of Mahler's, who proved that if you have a series like this, a rational series, any rational function, if you take a formal power series like this, which is a rational function, then there must be either alpha I is not equal to 0 for all I large enough, or there is an arithmetic series where the alpha i's vanish, or the alpha i's can only vanish in arithmetic series. I'm not saying this properly. This is a bit involved to say, but roughly speaking, it says for only certain finite for finite collection of arithmetic sequences. So the zeros occur in arithmetic series, have to occur in arithmetic series. And this would tell you that the prime numbers are not too far apart. They must occur in an arithmetic sequence, and that violates the density of the prime numbers. So I bungled this last step here, but roughly speaking, it says that if both this generating series for the deviations and the Poincare series are rational, then you can construct a rational function. You can construct a rational series where these coefficients vanish, the coefficients vanish at all prime numbers, and that it won't do. That violates this result of Mahler's. So that's Jürgen's argument. Okay, so you can read it in those notes that Jürgen has. I want to go beyond this. So in fact, so this brings me to now really the new part of the talk towards the very end. So all this is now joined with Ben and Greg. Oh, so by the way, let me remind you. So Jürgen's conjecture was that if the cotangent homology vanishes eventually, then assuming flatness, then it must be LCI. So of course you can ask what happens if you can also ask what happens if you assume more. Suppose the cotangent homology vanishes already from degree 2 onwards. Can you at least say in that case that things are LCI? And as far as I know, the only result in that direction is due to Bernd Ulrich, who proved that if S is Leachy and the cotangent homology vanishes in degrees 2 and higher, I believe, then it must be CI. He nods, he agrees. Good. Okay, so that was just to say that I'm focusing on sort of the asymptotic behavior and not really looking at what happens if you assume a lot more homology vanishing. Okay, so the story with Ben and Greg is that sort of our question is our guess based on what little we know from related results related to this question is that if the cotangent complex is not short, the cotangent homology must actually grow exponentially. So to make sense of this, I'll have to find a way to measure the length of the homology, and the simplest way to do it maybe for this talk is to assume that the rank is finite. The rank of S over K. So S is a finite dimensional vector space. Then, of course, all the cotangent homology modules will have finite rank. And we can talk about the growth of this sequence. So the question sort of we ask is, say, so again, remember, I'm just working over the case where, I don't need local anymore, but this is the key hypothesis. The question is, if S is not CI, so does the sequence grow exponentially? So Jürgen says that there must be infinitely many non-zero homology groups, but actually we suspect that in fact the homology groups must grow exponentially when you can measure it. Yeah, and also one can also ask about the cohomological version. Yeah, of the conjecture. So of course you could have asked the same thing, and Jürgen asked whether if the cotangent homology vanishes, eventually do you have complete intersection? You can also ask the cohomological version, and as far as I know, that is completely open, even if you assume that everything has rational Poincare series. So I don't know that, but certainly, if yes, then both 0 for all n large enough. I'm just stating the obvious. So this is again 0. I'm switching from n. 0 for all n large enough implies SSCI. So you would get Jürgen's conjecture, but also you would get it for the cohomological side, which, as I said, I don't see a way of proving, even if you knew that everything was rational. Okay, so this is really the question we've been thinking about. But what can we say, not just about non-vanishing or non-vanishing, but actually growth? And what we can prove at this point is that this is so. So again, this is all with Ben and Greg. So this is so if one, so both these exponential, actually I see. So maybe I should, before I do that, let me say a word about what I mean by exponential growth. So exponential growth means that there exists a C bigger than 1 such that the rank of this, let me stick to the homological version, is bigger than C to the n for infinitely many n. Okay, so Ramos has introduced this notion of curvature. So this is tantamount to saying that the lim sup of these numbers is at least bigger than 1. So this is, so let me, in Ramos' language, this would be saying that, let me use the shorthand, the curvature of this this graded module is less than 1. Oh, it's bigger than 1, So the radius of convergence is less than 1. So I'll talk about curvature being bigger than 1. Okay, so which is saying basically that there is a sequence of, exactly what I said here, that there's a number C, a real number C bigger than 1 such that the ranks are at least C to the n. Okay, so the theorem then that we were able to prove is that this is so if for a few cases, for example, if S is multigraded, so the defining relations are all monomials, or the embedding dimension, remember S is Artinian, so is no more than 3, or S is Golod. So which means that if the ring is Golod but not hypersurface. So this is saying for all these things, either the ring is CI, or the growth must be exponential in that sense, or S is something called generalized Golod, and I'll get to that in a second, in a bit. Okay, so for these families of rings, one actually knows that the cotangent homology grows exponentially. It's not just non-vanishing, but it's also growing exponentially. The one thing to note is that none of this gives you any new cases of Jürgen's conjecture because one knows things are rational and all the Poincare series is rational in all these cases, but you get more information. Okay, so I want to just give you a sketch and the basic idea as to how we go about proving this. So the idea, okay, so the easiest, maybe the one way to express what we're trying to do here is to consider the class. Let me call it C. By the way, notice that in my list of references, I didn't point to any paper that we are writing. It's because we haven't even chosen a title of the paper yet. So it's that much in progress. So all this is ongoing. So let me call it C to be the class of local rings as before. So rings such that S is S such that okay, so I can focus either on the one class or the complement, but let me focus on the class of rings where the underequivalent is growing exponentially. Okay, so the claim is this is basically that this class is everything which is not CI, right? So do we know anything in this class? Well, so the first example computation is that if you look at something like S polynomial ring in say D variables and factor out the square, then one can compute directly that, better have D bigger than 2, can check directly that S is in this class. So the underequivalent of such, so these are examples of Golod rings, but they're very specific. And you can actually even here, it's slightly tedious to check. Underequivalent is not easy to compute, but in this case, you can check that the underequivalent homology groups of S over K they grow exponentially. So this is one case, okay? So now the idea is, once you have one ring, can you sort of populate the class using some standard ring operations? So here's one such. So here's a theorem. Suppose you have a map R to S, and if R is in C, then so is S. Oh, flat map, of course. So remember, I'm just working, because I want to measure, I'm just working with Artinian things. So if you have a Artinian map, a flat map between Artinian local rings, and the source is in the class C, then so is the target, okay? So if the other equivalent for R grows exponentially, it will grow also for S. And then the other results that it's not, this is slightly involved, the proof is slightly involved, but the other results are not so hard to prove is that C is closed under tensor products and fiber products. And fiber products. Okay, so this gives you already some interesting classes of rings for which you know that the other equivalent grows exponentially. But to go further, this doesn't get you quite far enough. Even this sort of results don't even let you cover the monomial case. So to go further, you have to enlarge the class C to allow DG algebras. So basically, D algebras A of the form. So again, what would be the analog of this finite dimensionality, where the rank of all these are finite? Okay, so instead of just looking at rings for which the under-equivalent is exponential, you look at DG algebras. And you can introduce under-equivalent as before. You can look at DG models. And remember when I described the cotangent complex of a model, there was nothing, I did not say anything about, did not need to know anything about the homology of the model. So take a model for A and you can write down the cotangent complex, and then you can start asking questions about growth. Okay, so in this case, we have this result here. In this generality, we can say that if you have a map like so, suppose you have an extension of DG algebras where you adjoin only finitely many variables, positive or negative, odd or even variables, doesn't matter. Then A is in this class if and only if AX is in this class. So A has exponential growth for under-equivalent if and only if this algebra, which we might say P, has exponential growth. So here's a simple illustration of the power of this result here. So you look at S and you look at the Koszul complex on S. So K of S, so this is the Koszul complex of S. So which, you just adjoin by adjoining some exterior variables, right? So these are all degree 1. And D of Xi is Ti in the old notation. So what this result here is saying is that the under-equivalent of S would have exponential growth if and only if the under-equivalent of the Koszul complex is exponential growth. And this is interesting or useful because when S is Gollard, the Koszul complex is equivalent to a trivial extension. So V is a K-vector space, a graded K-vector space. So it's like this example that I showed before. It's like the square zero ring where you have square zero, right? Oh, you have a question?
I should be fine in Ubud with
What?
a card, right?
Okay. So this, and we know that
Says I don't have that much.
So this is in X by the direct computation, by a computation similar to one I mentioned before. I didn't actually tell you what the computation was, but I said that you could handle this case by a direct computation. And this case is exactly the same. It's really a square zero extension of K. So knowing this, you know for all Golod rings. And in fact, this agenda, so S is generalized Golod. Generalized Golod means that you have a finite extension like this, where this is a trivial extension like so. So immediately from that result and the computation, you see that we know the result. This is how you get the result for generalized Golod things. Okay, and how this helps for the multigraded case is that you can reach any multigraded case ring starting with a field and doing polynomial extensions and Golod maps away from polynomial extensions. So using these two, playing off these two results or some variations of these results, one can get to multigraded rings. So this is how one proves that all these rings are have exponential growth for under equivalent. So let me try to wind up by mentioning a few connections to other topics, other questions. So I've only focused on under equivalent, but in fact, the under equivalent. So remember, so S is going to be now. Let's say S is let me just stick to finite type K algebra. So just to keep things simple as before. So in general, these under equivalent homology modules, this is a direct summand of Hochschild homology, which, by the way, in this case, in our case, we can just think of as these extremes. Okay, so there is something called a Hodge decomposition, which tells you, again, I'm using characteristic 0 here, which tells you that the Hochschild homology of S decomposes into various strands, and one strand is the under equivalent. So this tells me that if the under equivalent homology modules grow exponentially, this means the Hochschild homology also grows exponentially. And this is relevant because this is connected with, this connects to some conjectures in rational homotopy theory. The V-K-Fourier conjecture in rational homotopy theory. So the results I mentioned have applications in rational homotopy theory because of this connection. The second remark I want to make is that just like under equivalent homology, the cohomology modules are a direct summand. Again, because of characteristic 0, there's a Hodge decomposition also here, which of the Hochschild cohomology of S over K. Okay, so once again, if you knew exponential growth of the under equivalent cohomology, you would know it for under equivalent homology. So if you knew the curvature of this is bigger than 1, this would imply the Hochschild cohomology groups also grow exponentially, but Hochschild cohomology is a commutative algebra. Actually, it's also is a homology, but this is a graded commutative algebra, and this would tell you that this cannot be Noetherian because of the Hilbert-Serre theorem. Yeah, if it were Noetherian, then the growth must be polynomial, given by a polynomial eventually, right? The Hilbert-Serre polynomial. So if you knew the under equivalent cohomology modules grow exponentially, you would deduce that the Hochschild cohomology groups would be Noetherian. So this is connected with this question which has been lying around, that suppose new. So okay, so there's some background. Let me just write it. If it's Noetherian, does it imply S is complete intersection? Okay, this question is also open, but from if you put together everything I've said, you get a positive answer for all those families of rings. Now this is interesting because when S is CI, so you know actually the second André-equivalent cohomology, which sits inside the Hochschild cohomology. So these are the Gulliksen-Eisenberg operators. So Hochschild cohomology acts on, so this is acts on these various X groups. And these are all finitely generated over, and this is finitely generated as a module over this. So for complete intersections, the finite generation of Hochschild cohomology is behind these the various support theories that Avramo and Buchwitz and others have developed. So this question is basically asking if it's motivated by these results or this line of research, whether you only have Noetherian property of the Hochschild homology if the ring itself is Noetherian. And the only way I know how to get to this is by looking at the André-equivalent cohomology, not Hochschild, but André-equivalent, because somehow André-equivalent is much easier to deal with because of things like the Jacobi-Zariski sequence and so on. Okay. So although I started the story from the André-equivalent side, I actually got to it from this Hochschild side. And that's a good place for me to stop. Thank you.
Thank you very much, Shri, for the wonderful talk. So thank you very much. So are there any questions?
I have a question. Can you hear me?
Yeah, go ahead.
So is there any relation between the rank of André-equivalent homology and the nth deviation?
The what?
Is there any relation between the rank of nth André-equivalent homology and the nth deviation of S?
Oh, this is what I just said, no? This is the homology. Well, the homology is a subquotient of the complex, right? So this is where I was talking about it. So the deviations are the ranks of the ranks of the modules in the complex, and the homology is a subquotient of this. So that's the connection.
Okay.
I don't know. Is that what you had in mind?
Yeah, this deviation is same as the number of variables we are adding in that Tate chain
Yes. This is what this result is saying. If you look at the Tate resolution of K over S, the number of variables that show up are precisely this relation. So this is what I was saying. Somehow the Tate resolution records, this records, the Poincare series records the number of variables on, records the free modules in the free resolution of K over S. Cotangent complex records the relations that define S over R. And there's a match between these two.
Okay.
Any other question, guys?
You proved the exponential growth of the homology. What's the relation to cohomology?
So the same techniques that we have seem to give you also the cohomological. So everything I focused on homology, but it seems that the same techniques give me also for cohomology. So wherever I can prove exponential for homology, I can prove it for cohomology. So there is no direct way to go from
No general application.
No, I don't see it. Unless if it's Gorenstein, but you know that. Yeah.
Do you get any conclusion about the other summands of Hochschild homology or cohomology, the higher André-equivalent? do they grow exponentially too? I mean, for those classes of rings?
Oh, I see. I didn't think about that. You mean the other strands, whether they
Yeah.
also possibly, yeah. So actually they might, because what we really have is a calculation on Hochschild, and we can generate Hochschild classes. Yeah, but I haven't sorted out the details. But really we do a computation on the Hochschild. You can see easily that it grows exponentially. Then you observe that you can pick enough of them on this standard equivalent strand, but maybe also in the other strands.
Yeah, I see. Okay.
Yeah, okay, good.
May I ask a maybe possibly stupid question about your curvature? I think it was on page 18.
Okay, sure. It's supposed to, yeah.
Oh yeah, let's see. Sorry, can you scroll the other way? You were looking at the ring where you divided by the square of the maximal ideal. Yeah. Oh yeah, right here. Did you compute the curvature of that? I mean, what's the value of C that you get?
Curvature of what? What do you mean?
Of this S, of the polynomial ring divided by the square of the maximal ideal.
No,
or did you
the other equivalent?
Just the curvature? I guess you're saying that the curvature of these D
you mean the curvature of the under equivalent cohomology modules, right?
Yeah.
So I think it's D.
Okay. Oh, it's D. Okay, it's really
Ben will correct me. I think it's going to be D. Yes.
Okay, interesting. And can you use these D star modules or these are under equivalent cohomology modules? Is that what you're calling them? Or
and yes.
Can you use these to detect other properties of Artinian rings like Gorenstein or?
No, they seem to be really tied to the CI. Yeah, at least I don't know.
Okay, I mean it's interesting that you can try to detect the CI property from that, but okay, thank you.
Sure.
And thank you for the very nice talk too.
Thank you, Chris.
Any other questions?
I have a quick question.
Another one? Okay.
Yes. So you assume unknown that you want to have the characteristic 0 for simplicity.
Well, not
sure,
quite
there are
simplicity.
lots of done with a positive characteristic.
Hang on. At this point, I stopped being for simplicity when I started talking about new results, because the calculation I'm doing are really with easy algebras. So up to part 4, everything I said, well, not Jorgen's. Everything, basically until I came to this Jorgen's conjecture, everything worked in arbitrary characteristic. But from this point on, I do need characteristic 0, because what I'm really talking about is these numbers in terms of models. Yeah, it's not just for simplicity. So all these growth estimates, exponential growth, I know how to do it in only for characteristic 0, because I'm really computing growth of some other invariants.
So do you know any examples that in positive characteristic that you can easily get exponential growth?
Oh, easily. I see. So your question is whether I know that I can, some examples where I get exponential growth?
Yeah.
In positive characteristic for trivial reasons.
Positive characteristic case.
So there are some operations on, yeah. So in positive characteristic, there are some extra operations, but I don't have a clear answer to it.
Okay.
Okay.
And so your cotangent complex, so here, which is defined only up to homotopy equivalence. But in many places, you say that L equals 0. Or Li or Ln equals 0. Everything is.
So what it really means is that actually the way I could have avoided, if I have to be more careful, I could have talked about the cotangent modules, the CNs that I mentioned. So really what I'm saying is that this CN is projective or something.
Right. Okay.
Really, I should be talking in terms of the vanishing of these functors. This is unambiguous.
I see. So the rank of the CN still depends on the choice.
Oh, no, not this, not this, not this. This doesn't.
That one doesn't, yes.
Yeah. But so what I would say is that if Cn is projective, so that doesn't depend on the choice, whether these, because maybe I did not say it here, I should have said it
So
here. This is well defined up to
rank of
projective.
the co-kernel is not
It's well defined up to projective summand. So everything one should be looking in the stable category or something, then it's okay.
okay.
Yeah.
Okay, thank you.
Yeah, okay, I did remember one thing. So in characteristic P, so one can actually use some, there are some extra operations you have on the cotangent complex that one
It's a
can use.
divided power structure.
Yeah, so these Dyer-Lashoff operations and things like that.
Mhm.
One can use to prove, so analogs of the Steenrod operations that one can use to prove that in characteristic P, infinitely many things are non-zero, but I haven't seen it written down. One of my PhD students was supposed to be sorting it out, not done yet.
I thought the Tate's construction of the resolution is somehow also constructing the cotangent complex. Am I right?
What was that?
Tate in 1957
Yeah.
on the homology, and he constructed a systematic way,
Yes.
constructing the resolution.
Yeah. This is what I was referring to when I talked about models. It was really Yeah, exactly. This is Tate.
So that's exactly Tate resolution.
Yes.
Tate resolution.
In characteristic zero, yes, it is. Yeah. Otherwise,
Yeah, this is in characteristic zero case, but in characteristic P,
divided powers. Yeah.
that's much more complicated. Okay, thank you.
Of course, Andrew. Nice to see you.
Yeah.
In a while. Okay.
Srikanth, I think if there are not, let's wait a second because it seems people pop up with questions. Okay, if nobody has more questions, then we would like to thank you for the fantastic talk again.
Oh, thank you.
Yeah,
Great
thank
talk.
you. Great talk. Very
Thank
interesting.
you. It was great talk, really great talk. Okay, guys, since we are gonna see each other in a month, I think, no?
Even less. I think December 4th or whatever that Wednesday is the next one.
Perfect. So let's see each other December 4th, guys. Okay. Bye, everyone.